Hello everyone and welcome back to the series of Digital Logic Design. Today we will study complement of a function. The complement of any given function f is represented by f prime and is obtained by interchanging zeros into 1 and ones into 0 for the value of f. If original function have a value of 1 for any binary combination, so its complement will have a value of 0 for that particular binary combination. Or the given function have a value of 0, so its complement will have a value of 1 for that particular binary combination of the variables. The complement of a function can also be derived using De Morgan's theorem, which says that for any two variable x and y, x plus y whole prime is equal to x prime dot y prime and x dot y whole prime is equal to x prime plus y prime. Now the De Morgan's theorem can be extended to three or more variables. Now starting with any three variable a, b and c, the first form of De Morgan's law can be derived using the postulates and theorems of Boolean algebra. For instance, we wish to find a plus b plus c whole prime, so we will use a substitution which says that x is equal to b plus c, and the equation will be reduced into a plus x whole prime. Now by first law we know that a plus x whole prime is equal to a prime dot x prime. Now substituting back the value of x, which is b plus c, we will have a prime into b plus c whole prime. Now again applying De Morgan's law, we will have a prime into b prime dot c prime. Now using associative property, we know that changing the order won't affect the result of multiplication, so this will be equal to a prime dot b prime dot c prime. Now the De Morgan's theorem for any number of variable resembles the two variable case and can be derived using the successive substitution, and the method is similar to the case of three variables. So the theorem can be generalized as follow. The complement of sum of variables from a to f will be equal to product of complement of each variable, where the complement of product of variables from a to f will be equal to sum of complement of each variables from a to f. Or we can say that the generalized form of De Morgan's theorem states that the complement of function is obtained by interchanging the logical operators and or and complementing each literal of the function. Now in the given example, you have to find complement of Boolean functions f1 and f2. For this we have to apply De Morgan's law as many times as necessary. The function f1 equals x prime dot y dot z prime plus x prime dot y prime dot z and is sum of two terms. Now its complement will be f1 prime will be equal to x prime dot y prime dot z plus x prime dot y prime dot z whole prime. Now using De Morgan's law, the addition will be changed into multiplication and we will take complement of each term. And within each term the variables are getting multiplied, so we will have a relation in which terms will be added. So the equation will be x double prime plus y prime plus z double prime into x double prime plus y double prime plus z prime, and we know that complement of x complement equals x, so we will have x plus y prime plus z into x plus y plus z prime. Now same rules of De Morgan's law are applied to the second function, and solving this we will have x prime plus y dot z prime plus y prime dot z. Now in generalized form of De Morgan's theorem, we said that the complement of a function is obtained by interchanging and or operators and complementing each literal. Now here, interchanging and or operator is similar to finding dual of the function. So a simple procedure for deriving a complement of function is to find dual of the function and complement each literal. This method follows from the generalized form of the De Morgan's theorem. Now for the last two examples, we will find the complement using the generalized rule. For both functions f1 and f2, at first we will find dual of the function and then we will complement each literal, and if you compare the results, both are equal. Thanks for watching the video and stay connected for more interesting videos.